Okay, welcome back. I know we've had a week off, so most people don't remember what we were doing last time. Last time I saw you, I was trying to introduce to you how to actually use GLUT and OpenGL in terms of making simple Hello World programs. And I brought up a simple example, and the simple example showed the components of the OpenGL program and how to create the different functions, and it's in the first part of Lecture 2A. And then I ended kind of saying that I was going to essentially bring up, go get some more examples, bring up, do some minimal link searching, and bring up a list of extra stuff for you guys to do to learn the concepts. Because I'm a strong believer that example, program by example, especially in this particular case, works out quite well. Because no one can actually teach you how to program. And OpenGL is kind of interesting because unless you get the pieces correct and you follow a certain format, in terms of setting the plane correctly, basically creating the right objects, putting the right objects in perspective with the other objects and things, it can actually get kind of hairy doing it from scratch. So what I've done for you is I've made some bookmarks here, and I didn't write them down, but you can write them down if I make them big enough. One of the best places to find examples, and all of these examples are going to work in your Dev C++ compiler, and I'm going to show you how to actually make them work, because there's a little trick to it, actually. But this one is at the opengl.org, which is the best resource actually, because this is from the research. So you can don't get their OpenGL version, what you've got, your GLUT version that you've got in Dev C++, is this. This is what you're running actually. So if you go to www.opengl.org, resources, code, samples, GLUT_examples, examples.html. It's a mouthful, but I'll leave that there for a few minutes while I gibber a little bit here on other stuff, just so you have an opportunity to write down, or if you want to, you can go out and get the video, pause the video, write down the URL. This particular source is going to be a great learning tool to actually look up examples, which is why I like it. So I'm going to assume if those people who are going to write it down have written it down. If you go into the source, you can download everything all in one zip file. And the zip file, it's essentially going to be up to date with all of the different stuff that's on the screen. What's on the screen? One of the reasons why I really like this is because each one of them is sort of, it's all in C files that's going to work. And each one of the examples is kind of self-explanatory. It basically explains, like for example, this first one demonstrates the use of the external Evergrabber, which is going to be the image data that's used for RGBA formats to draw pixels. So it's going to show you all about the color system in terms of the RGB scale and all of the numbers and essentials for that. Here's another one for a bitmap font that's going to be font oriented. I'm not going to go through all of them, but just as an example, simple cubes that are drawn with minimal OpenGL calls. So what you end up with is the screenshot. You end up, so you can actually see what the program does. You end up with a source code. You click on the links. If you don't download the, I'll just download this one actually right now. If you don't download, I'm going to put it on the desktop. If you don't download the exe file, you'll have to download the individual links. And this simple cube here, this red 3D cube I just clicked on, and I'm going to actually just, where's my red cube? Here it is. Here's my cube. I'm just going to double click on it, and it's going to bring it up. Hopefully at this point you've got the software installed. If you don't, you're behind. It's pretty well documented. I've actually not looked at the cube, so I'm going to find out real quick here. No, it is pretty well. It's a program for distributed, OpenGL stuff there. Red diffused light. So this is what I mean with these examples. They're made for teaching. They're made to be used to understand the concepts. So it's going to be documented like this. So we've got the normals for the 6 faces of the cubes, and the vertices for the cubes, and filling in the polygon, and then we've got the void draw box, which is going to be the function that's going to set, and we're going to go down here, we're going to have a display, and then we have our init that's just going to set up the plane for us. And I'm not going to go through all of this example, but it's going to run through. In fact, our init main is going to do everything. It's going to run the init, it's going to run the glet main loop. It's going to be very, very textbook-like. It's not going to do anything fancy. It's not going to, because what ends up happening with a lot of the examples you find on the internet, they're using third-party packages, they're using non-standard OpenGL tools and things in there, and it's not well documented. It's hard, they're all convoluted. You can't really tell what it's all about. So that's one of the reasons why I like this particular website. If I compile it, I'm going to demonstrate a problem to you. Here's the problem. The problem is it's a linker error, which is what you're going to get. And the linker error has nothing to do with this guy here. It's that we didn't specify that we're going to use the OpenGL library because I didn't create a project. I just double-clicked on it. And I did that and I opened it up in OpenGL without creating a project. I'm going to show you live here how to fix this actual problem. You could do one of two things. You could go like this and OpenGL, just open Dev C++, select new project, and do what we did before with that little example. I'm also going to show you two things. So we're going to new project, and I'm going to pick a multimedia. I'm going to go OpenGL. Actually, so just go glet, because I think that's all you have in yours. You might have OpenGlet, you might have OpenGL. It's glet. That's all we need. It's going to be the same thing essentially. And I'm going to save this to the desktop. I'm going to call it cube. Cube.dev. Oh, I think I spelled that wrong. Cube.dev. Let it to desktop, I believe. It's stayed on the desktop somewhere. I don't see it. Well, I'll save it again. And in here, if I run this, I've got main in here. Instead, what I can do is just remove this file here. Or I could cut and paste it if I wanted to. I don't want to save it. No. So. Oops. Remove file. Save changes. No. Okay. And then I'm going to right mouse click and I'm going to say add to project. I'm going to add that cube. Oh, you know why? Because I saved it in dev. I didn't save it on the desktop. That's why I didn't see it. Here's my cube. I'm going to say OK. Now if I compile it, I'm actually going to get a successful compilation. I'm not going to get all those linker errors. So as an FYI, what I've tried to demonstrate to you is how to avoid the linker errors that you're going to get when you double click on these examples. And it's just a dev actual problem. So if I run it, it's going to come up and show me that little cube. And the cube doesn't really do anything. The cube is just sitting there. So that is how you would essentially create a project from a non-existent project if you wanted to. Another trick you could possibly do if you wanted to, and I do this occasionally when I get sloppy, is I'll take one of these other projects and just copy anything that has an OpenGL project type to it, a multimedia type, the project file itself. You just go like this and go, I'm just going to do this, copy, paste, and call it cube, because I saved the cube in another directory. A view cube. It's kind of a, if I double click on cube, it's going to come up and I'm going to see that older file. And you can put more than one file in the project as well, but then I'm just going to go remove here. It's not going to remove it. It's not going to remove it from my desktop. It's just going to remove it from the project. And then I'm just going to add to project. And what am I going to add? This cube file. If I do that, and then I've got, and this one's actually called Hello World. If I wanted to, I can change the name of this, go into project options here and call it cube. And then this is essentially going to compile just fine for me without any linker errors or problems. And it's going to run just like it did before. So keep that in mind when you start downloading examples, just FYI. Otherwise, you're going to run into a bunch of linker errors, especially if you start using OpenGL like that. Okay, so the best tutorial on the internet as promised. I'm going to give you some extra, because we don't actually have a book for this course. Instead, what I'd like to do is put you in the right direction. The best tutorial on earth is this one. It's actually called it used to be called the Red Book. And it's made again by OpenGL. It's glprogramming.com, and oops, let me focus in on the URL here so you can find it. Simpler URL, glprogramming.com/red, because it used to be called the Red Book. In fact, actually it was published. In fact, it's out in publication, but it's also available and freely downloadable from the source. What do you get with the Red Book? Not only do you get a bunch of examples, but you get a full book that is probably the easiest OpenGL book on the market. So if you click on it as an example here, OpenGL, you're going to get explanations for, and then it's all sectioned off. It's really well organized, and it's clickable. So, you know, what is OpenGL? You can click on it and read all about what OpenGL is. And then you've got explanations of each one of the different, you know, differences between the wireframe and the solid models and all as an example that's going to be in here. And then on the bottom you get a smidgen of, they call it a smidgen, so like a snippet of OpenGL code. So not only do you get a tutorial with it, but then you get the code that goes along with it. So it's probably even a better resource. The only difference with this is you have to go through a lot of reading, and it's meant to be a tutorial. It reads like a really excellent textbook, actually. So one of the things I'd like you to do if you're interested in doing well on the homework assignments is to, and unfortunately, you know, this class has got a lot of outside kind of self-study mode to it, because the only way you can really learn how to do this is to play with it. Until you start playing with it, you're going to have absolutely no idea what I'm talking about. I mean, I can implement concepts for you and show you examples, but it's not going to help you learn it. So one of the things that I would do is just start reading through this and start, in fact, once you get about halfway through it, you're going to find, oh, I know this stuff, and then you'll start picking it up on your own. Because once you get to about the texture mapping point, after you get past the basics, the lighting is kind of interesting. Color, so there's an entire chapter on color. There's an entire chapter on lighting. And the slide set that I have is based on this. It's based on this Red Book. It's the slide set that comes with the Red Book. So what I'm going to do throughout the remainder of this course, as we get past the basics, is go through the concepts as an example of color and the concept of lighting, and go through each one of these basic and give you the concepts. But it's kind of up to you to sort of figure out how how you're going to implement it, what you're going to do with it. I've got another link here that I'd like to show you as well, and this one's called OpenGL Colony, and it's kind of an interesting link. The reason why I like this link, by the way, was just another link. No, actually, this one's subject, instead of, this is more advanced. Let me actually zoom in a little bit here. You could go to opencodecolony.de/opengl.htm. Actually, let's just do it this way. And you can get to the same page, I believe. Yeah, it's the same page. This is what you want to write down if you're going to do it. It's an international site. This particular site I like for a couple of good reasons. It's more advanced, and there are tutorials with the examples, and all of the source code is downloadable. And as an example, if I want to search on, for example, I think I had searched on actually transformation, which is why that link was different. If I go down here, like transformation part 1 and animation, if you have problems, let's say, for example, with figuring out how to get the keyboard input to work or how to get the mouse to work, there's really good examples, and this one here I've actually downloaded just to test out, just to make sure we're still compatible. And not only do you get a complete tutorial on it, but you get the source code and then ultra descriptions about what these function calls are actually doing. So what you do, and because each one of these is separated out by transformation 1, transformation 2 as an example, using a camera, simple user input as an example, and there's a slew of these, there's like millions of these things out here. You basically search on, what do I want to do? Well, create a robot, or I want to, lighting or color or something, and you're going to have more advanced examples that are going to go through tutorials on particular techniques that you're interested in implementing. So, highly recommend. It's another good source. And as an example here, I took this transformation one, part one, and I, oops, let's see if I can get my screen back. And I downloaded it here, actually called it transformation. And again, you have to make a dev project for it, which I've already done, so I'll save you the time on that. And here's something that you're not going to get from the other site. It's basically the ability to take, this particular example is going to use the mouse, and you'll be able to zoom in and zoom out through the plane. And it's called a transformation as an example, and I don't really expect you to, I'm not going to go through the source code actually, because I'll wait till we start talking about transformations, which is coming up soon. But transformation is nothing more than a calculation. In fact, the source code for this, I'll just show it to you because I have it up. Not too bad, actually. We have the display function, the reshape, we have the main. It's doing nothing more than doing an idle, this is a rotation. So we're taking the XYZ plane and we can rotate it to the left, rotate it to the right. We can zoom in, we can zoom out through any coordinate system on the plane. And the transformation component of it is nothing more than taking the metrics of the point positions and adding 3 to them, all of them, or multiplying something or adding something to them to transform the position from one location to another location. In this example here, it's just adding, it's setting the rotation to be altered when and actually I'll just show you what the code looks like, because then you can kind of get a feel for it. Let's see, let me just run it. Oh, no, this is the wrong one. What did I do? I'm looking for a different one. Well, this one is transforming on its own, actually. It's not taking my mouse input. I have my examples messed up. There's another one I downloaded from the same site. This is doing nothing more than setting the state machine to perform the calculation of, in fact, maybe I can overlay this so you can see the rotation here. And the rotation is going to be setting this idle calculation. And it creates a form of animation, but it's really a transformation, because we're just taking a solid figure, so it's a wire, we're taking a wireframe of a figure, and we're rotating it on the plane using the state machine to redraw it. So it displays it, resets the coordinates, displays it again, resets coordinates. And in essence, we've created some pretty interesting animation, essentially. But it's using what's called transformation as an example. So if you go to the website and actually kind of go through the examples, it explains the concept for you as well. I'm trying to think, the one that I had, I think it was called events, actually. Let me just see, now that I mentioned the mouse one. Because what you're going to do is when you start looking at, if you haven't done it already, I would highly recommend starting to go through some of the programming assignments for the course. The first one I've actually already talked about with the setting the cones. And I have one actually I can show you in a few minutes that will help you with the cones for the windmill with the rolling hills. And it sounds very complicated when you look at it. In fact, it scares most students. How am I supposed to create a windmill with rolling hills? How's that going to work? But you're going to create a windmill that is like made out of a cone with another cone on top of it. So it's going to represent a windmill. And the rolling hills are just going to be more cones. And you can actually do the whole thing with cones if you wanted to. Because you're representing the concept, you're not creating, like if you were to draw a picture, a painting, you're not actually creating, oh, that's just a warning, okay, good. You're not actually going to be creating a graphic, okay, so I'm going to zoom out a little bit, a graphic kind of program with this. So this is the transformation that's occurring with the positioning that's related to the mouse. So I'm dragging the mouse, I'm clicking on it and dragging it this way to make it smaller, clicking on it this way to make it bigger. And These are built-in shape. The teapot is actually a built-in shape. So you didn't have to draw the teapot on your own. You say, create a teapot, essentially. So this particular example that came from that same website is showing you, and it's labeled for mouse. So it does a mouse transformation with mouse drags and drops and pulls. You can also get ones that respond to show you how to do the keyboard input as well. So this isn't really a programming course, it's OpenGL, but you don't actually have to have that much programming experience. Some basic, not being afraid of it, actually, some basic, along with a ton of examples, will definitely carry you through just fine. Let me think here. The Hello World actually went through before. Where are these examples now? Which is a good question. If you go to the bhacker.com site, which is where you're going to find actually the programming assignments I keep talking about, you're going to notice that down here, graphics, programming examples, I've selected a few here that are going to help you with the programming assignments. So these are designed here. These are not the ones that are on the website that I've just shown you a few minutes ago. These are different ones, and I'm going to show you the robot in a few minutes. So I'll talk about assignment number 2 in a few minutes. But things about, in terms of events, that was the mouse one I just, no, actually that's a different one. Moonlight, light, shaping, 3D transformations, things of that nature. These are the examples that you're going to use as a resource to sort of help you with the assignments. So. Now, I've kind of talked about, for those of you who weren't here, you missed it, but I've sort of already gone over the first assignment for this course, and whoops, wrong class. Let me get the right class at least. The first two aren't too bad. In fact, here's our humanoid. The first one here, because I sort of want to show you this so that I can relate this to some of the examples. Show you why I'm pointing this out to you. It will make your life easier. The second example, first example, the point was to see if you could figure out the plane. So, in order to make rolling hills in a windmill, the concept is you're creating an object that's kind of close to you, sort of, and then behind the object you're creating rolling hills. And the hills should be sort of flat this way, and the windmill should be like this. So the biggest thing with that is that you're not going to create something that looks like rolling hills, and you're not going to create something that looks like windmill, as I mentioned. You're going to put some shapes together, which is what we're doing here. So that purpose of that was the orientation of the two objects, or a couple of objects, on the plane, so you can get the viewpoint correct, and to have you actually create some shapes. The purpose of the second assignment is to get you familiar with shapes next to other shapes. So you can create a humanoid using, in this particular example, it's got circular circles or spheres. Or I'm going to show you one with logs with rectangles, and where you can actually stick the pieces together. And these are all different shapes that you're creating. Obviously, you're maybe not going to want to put eyes on there. I don't know. You may not have a neck. I don't think my humanoid's got a neck, but I have a humanoid, for which I just showed you a few minutes ago at the bhacker.com website. You can see the source code example for it. So I'm giving you the code for it. So what are we going to do in this assignment? Assignment is intended to familiarize yourself with a hierarchical 3D modeling transformation. So instead of taking the pieces and putting one in front of the other and just getting them on the plane, now you're creating a hierarchy. So the hierarchy is accumulation of things that are connected to other things. And that's what I'm going to start actually with the lecture, talking about hierarchies and basically building shapes to work with other shapes in terms of creating objects. So a humanoid sounds pretty sophisticated. You can create one quite easily by creating a bunch of rectangles, and squares, and circles, and putting them together in the plane. You assemble them in a hierarchy. And then if it's in a hierarchy, if you move the arm, you can send the movement, and my robot actually moves. My humanoid actually has one arm that moves, because I only put the operation on one arm. But In the hierarchy, you can send it down from the shoulder all the way down to the bottom, as an example, or from the legs. So you can get your humanoid to walk. You can get your humanoid to do all sorts of different things, which is kind of interesting. So the assignment is intended to familiarize yourself with the hierarchical 3D modeling, transformation, and the lighting. Also lighting in OpenGL. In my examples, I'm going to show you lighting, and I haven't really talked about lighting yet. So we're getting there. So you're going to write a program to display an articulate humanoid created with ellipsoids and selected appropriate lighting and materials. You can use any material you want. You can use any shape that you want to create your scene. So you're going to use OpenGL and the GLET functions for the modeling of the humanoid and the lighting scene. And you're going to use a mouse and keyboard for input events, which you're going to actually pick up from the first assignment, which is going to get you oriented to the mouse and keyboard. You're going, well, I don't know how to find. Go through the Red Book. You'll find easy, simple examples in terms of that. So you need to set up a viewing and a projection transformation. The projection transformation, as I just mentioned before, because this lecture today is kind of twofold, to give you the terminology and to present some examples of these concepts. I just showed you the transformation. The transformation is when that cube, that wireframe cube, moved. We're taking the matrix and we're doing some matrix addition to it to basically redisplay it at different coordinates, and then redisplay it at different coordinates, and then we achieve animation from that. Well, the same thing actually is the case when you're moving an arm, and in a hierarchy you can move the whole. You can nest the arm, and inside of the arm have the forearm, you have the top of the arm, the bottom of the arm, the hand of the arm, and you can separate it out in terms of a hierarchy, and then take the whole thing as a grouping and transform it, which means you can get the arm to swing in a circle by not working at each one of the individual shapes, but the composite of the hierarchy, which is the trick there, which is what this assignment's all about. So specific project tasks, you're going to write an OpenGL program to draw the articulated humanoid, effectively known as the egghead. You can call it anything you want. So the humanoid is actually in figure number 1. So you have the head and the neck, torso, 2 shoulders. I really don't care. If you can create something that looks like a humanoid, perfect. You don't have to follow these instructions to the point. If you want to learn the most, implement it to the point. If not, hack it. Create a humanoid. And you can use the humanoid I'm going to give you in a few minutes. Each body parts, except for the hip, can rotate with one degree of freedom. So any configuration of the egghead is specified with a 13 angles that are associated with it. So you can use GLET solid sphere to draw the sphere if you wanted to. Transformation specified for the figure will go as bottom. So you want to draw the humanoid with its hips centered at the origin, 0, 0, 0. So the humanoid is facing forward, essentially. Select the initial camera location. So you're going to cast a shadow on the humanoid, so he's in the spotlight, essentially. And the pointing down -Z axis, and let the default projection mode be the perspective mode for that. The dimensions of the body of the humanoid are specified in Project 2. So I'm giving you support files. So that means you go out to the website and you can actually find this particular file that you can use, and these are, again, they're all dev C++ files. So it's available from the course website. You also find the other code. You'll find animation code, and you'll find humanoid code, which I'm going to show you in a few minutes. So it sounds like a lot of work. However, I'm giving you all the pieces. You just put the pieces together. That's how this works. So in the default configuration, all the angles are set to 0. So in the touchdown position, because you can actually get your humanoid to touch the floor if you wanted to, the hands, which is kind of interesting. You're going to find it helpful to draw the X, Y, and the Z coordinates. So here's our picture of our humanoid. This is using the ellipses, it looks like. So the humanoid, initial drawing, the angle is set to 0, because he or she is facing forward. The 0, 0, 0 on the axis. And the good thing as well, you don't have to put any other pieces in the axis, you're just drawing a humanoid. You don't have to actually assemble anything else for this. The second part of this is on the lighting scheme, and I'll kind of wait with this one, because you can do this in 2 steps. You can create this one, actually you can create this one at the same time that you're creating your windmill. It's because pretty much because you could take your windmill, and instead of the windmill, you put the humanoid there. You get rid of the rolling hills, and you're on to assignment number 2. And it's going to have you apply some light. So I'm going to save the lighting. I'm not going to go through the lighting right now. I have a whole lecture on lighting. Let's take a look at an example here that can be downloaded from the bhacker.com website. It's 3 files. One of them is going to be called Robot. Maybe I should have called it Humanoid. But the Robot one is a little tutorial transformation. It's going to rely on a matrix for all of the mathematical calculations. So OpenGL is known as matrix stack, which comes in handy for constructing these models. Simple objects like a robot can be constructed. So we have the model view matrix, which defines a coordinate system that's going to be used to place the objects in orientation with the other objects. So we can take a 4x4 matrix, multiply the matrix multiply it by the vertices and transformations to create new matrix that reflect the results of the transformation, and apply it to the vertices, and essentially we can create animation with that, as we've shown before. So you want to modify the model view matrix. We use the GL matrix mode. It's defined, and here are the methods for it. So this support file is giving you the methods that is doing the translation for you in terms of the matrix calculation. So let's take a look at the humanoid, and you'll go, "Wow, you gave us all the code." Yes, I'm trying not to make this difficult for you. But even giving you the code, you're still going to look at it and go, "I don't understand." Alright, so here's my robot. My robot is taken from an OpenGL game programming example, and I've left this reference in here so that you can go look up if you want the rest of the game. This is just one of the robot figures that appears in an OpenGL game, which is kind of interesting. It's nothing more than a bunch of cubes. So we draw a cube, and then we build a hierarchy, and you can see this cube is, here's the top face, the front face, the right face, the left face, the bottom, the back face, and this is just the face. And then we go through with, draw the arm. So we draw an arm. So set the color to red, create a 1x4x1 cube. So it's all done in cubes. And then here we have to draw the head, the arm, the torso. Here's our torso. Here's our leg. Draw the legs. All the code is the same. It's all cubes. We're just setting different. We're setting different coordinates on the system. We're placing it in relationship with the other coordinates on the system. So here's our void draw robot, which is going to put all the pieces together. So it takes the state of the robot legs. True means that the legs are forward. False means that the legs are backwards, because we can actually change forward, backward, switch the robot around, make some animation with it. And down on the last but not least, we go through the regular old stuff, the transformations that we're going to do for the legs. And what we can do, in fact this is kind of common to see it done, is you can have functions called rotate left, rotate right, head up, head down, kind of like a remote control. And you essentially run the functions to animate the behavior, and all you're doing is performing some transformations in the matrix. So let's see it work, actually. Yeah, if you download it, and I've also put up the dev project file for this as well. Here's our robot. He's in a state machine, and he's rotating around, and I believe one of his arms is going to go, yeah, here. One of his arms is going to go up and around. I left out the neck. There's no neck. It's a necklace robot. And it only has one for everything. You could separate out the cubes. You could separate out you can't see that I have ferment there. You can, if I were to extend on this concept, I'd put two pieces for the arms, 2 pieces for the leg, because he can't really bend down. So you could make him fold up, bend down. I'd maybe add a neck. If I added a neck, you could probably see that the head's also been rotating, but you can't really tell because of the. You can sort of see the head, and one head and one arm is actually rotating. So, no, I take that back. both arms, both feet, and the head are all rotating. But one arm's going in one direction, the other arm's is doing something slightly different. And the robot actually pretty primitive, but you can take this as a base, add the lighting to it, add whatever you want to it, and change. And basically, it's going to demonstrate what you need to know and the functions that you're going to need to call for the second programming assignment, which is going to be all about the transformation that's going on with the robot. Questions about the second assignment or the robot? This is fun. OpenGL, you can do a lot of fun. This was not what was in a video game, actually. This source code came as an example of how they did the robot in the video game, obviously. This doesn't look like a high-quality robot, but looks pretty fun. So. All right. Unless we have any questions, I'm going to close the examples up and move on to finishing up this lecture that I've been going over for the last 3 weeks. And the lecture, we ended up on slide 74. Yep, perfect. Let's see, there we go. So I'm not going to start it off from the beginning, but let's finish this up, and that'll be a good accomplishment for this evening. The lecture, if you're not familiar with it, is based on the Red Book, as I mentioned before. That's that website I showed you. So if you want more specific information, that's an excellent resource to go through it. And the purpose of this lecture was basically to go through everything about OpenGL in terms of its features. So next week, when I get done with this lecture next week, I'm going to start in with the different concepts, like texture mapping, buffering. Actually, I'm probably going to start with color and lighting first. But the lecture itself is about 100 or so slides, so that's why it's been taking so long. Going through the history of OpenGL, and there's the reference to the best site that's out there. OpenGL, in terms of the concept of the state, the notation, if you remember this right, if you've missed some of the class meetings, went over the concept of the functions and the different pieces of the name. And what's different about OpenGL is it's not object-oriented, it's functional, and each one of the functions is self-identifiable. And the function names are self-identifiable, which is kind of interesting. There's a code, as I went through before, that will tell you which function is doing what, and also, you know, the level of parameters and the things that you have to actually send as function calls. So it's helpful if you know something about function calls. You don't have to know anything about object-oriented programming. You don't have anything to know about data types or anything, because you're really not using any. You're not using variables. You're not really doing anything like regular programming. Instead, what you're doing is a bunch of function calls after function call. So I've covered this already as well. These are the precompiled headers, and you're going to use the one that is going to be working for you, hopefully, with the OpenGL interface that you've got installed. You don't have to use dev C++. I'm giving that out as an option as one of the easiest ways of getting up to speed. If you want to use a Microsoft compiler, that's fine. You have to download and install OpenGL on your own. So, and if you happen to have missed that, I went through the entire concept, how to download and how to configure the software. You can find it in one of the previous videos that's been recorded for the course. A couple weekends ago, in fact, actually, no, this is the last lecture, I went through the simple program. In the simple program, the code is downloadable from the bhacker.com website. And this was basically going through the different parts of setting the state machine. It's common to see a display. This one's called My Display. Sometimes it's called Display. Basically setting the object for the display. And then in the main, we have a loop. We have glet main loop, which is a function call to say, do it over again, do it over again, do it over again. So main never stops. So we don't have like the imperative programming environment that we have in normal C++ programming. And you can do this in Java, but my lecture examples are all C++ related. There are some glet and OpenGL libraries for Java, however. In fact, they work with the Android operating system. Anyway, back to this, however, the basic functionality, this is the simplest of our hello world, essentially. If you just picked up this course, first time you've been here, you want to go through this example, essentially, to figure out, you know, the concept of the event loop, which we've covered so far. We've also covered the concept of viewing in colors and window parameters and things, setting the title on the window, as we've seen so far. The program structure itself with main, defining the callback functions, what those were, opening one or more windows, entering into the event loop, which is, so in an OpenGL program, especially in the basic format, every single OpenGL program runs the same way. It just has different shapes. They all work with the same coordinate system. They all work with the same functionality. So the init, so we have main, init, and callbacks essentially, and then we essentially fill in the pieces and then start the loop, and voila, we've got our program that runs. So the common thing I normally see when students haven't gone through this lecture is they'll create a for loop and they'll have an object print to the screen. That's not using OpenGL. That's using a for loop, which is kind of memory intensive actually when you do that, because you can essentially run out of memory and your program's going to die. Because the glut main loop is actually designed as a function to permanently, constantly display in a loop your main and your display, whatever you have set in here. And your init is going to open up and initialize the OpenGL state. And this is actually making better use of the memory and better use of the processing speed, which makes an OpenGL application, if you run it the right way, using the right function calls in the right kind of format, as this lecture kind of demonstrates, you're going to get a faster running, more efficient program that's not going to bomb out on you. If you download an example and your example is freezing up, it means they're not setting the loop correctly, or they're not initializing something correctly. Also went through the main glut functions, and these are the functions that you're going to be using over and over again. So this is slide number 38. It's got everything that you're going to essentially be going every single program that you write. In fact, this went into an explanation of each one of these. So the following slides go through the glut int, the glut display, display mode, window size, setting the position, setting the initialization essentially, the color, foreground color, background color, projection, and things. And then I also talked about the coordinate system already as well, and the OpenGL camera and the camera angles. And I touched a little bit on the transformation and viewing. Didn't show you the examples. Those are the examples I just showed you, actually, on the transformation. And 2- and 3-dimensional viewing from camera angles. I've got some examples to show you that. MyDisplay.c is one of them. Actually, it just takes a polygon and throws it out. We also I also went through a lot of the different primitives. These are shapes that you don't have to reinvent. They're primitives. It's kind of like primitive data types. They're in the language. So you just create a new polygon, create a new strip, create a new line. And some of the issues that were associated with it in terms of the angles and certain edges that can't be accessed and things. So sometimes it makes more sense to actually create your own shape by combining shapes together, as we saw with the robot. The concept of the attributes being applied, some of the primitives to begin to end, specifying the primitives here, and here we have our coordinate system, our x, y, z, w, which is our primitives that are described in terms of these vertices. And this is where I'm coming into that transformation metrics, where we do a calculation on this coordinate and we automatically switch and we've rotated the object. And then if it's in a state machine environment, we just do you don't even have to run a loop for that. You just do the transformation once, and then every time it loops through, it does it again, does it again, does it again. So there's no looping that needs to be created for that. It's automatically in the main state machine. Let's see. Specifying the OpenGL vertices here, recalling the geometric primitives. And it doesn't really take that much of a geometry. You just have to be familiar with the X, Y, Z, W plane. Or if you can get the X, Y, Z down, you've got 2-dimensional graphics. So you can work it to the 3-dimension, and you can work it further. Looking at GL points, setting a point size, actually drawing something. We looked at this as well. This is by drawing 4 points and then filling in with a color in between, creating your own square, essentially, using GL quads. And essentially, this is going to set the coordinate system for the relationship of the points and how they're set on the grid. So. And believe it or not, there's programs out there that you can draw and it will give you this stuff. So most of the time, the first thing that students find more difficult is, how do I know where these points are? How do we set these points? Then you look for one of those open source tools, and I've been meaning, I have to make a note to myself, I will find a couple of those open source tools where you can draw shapes and it gives you the coordinate system. You just plug the coordinate system into your program, and you have the right shape, you have the right size, and it fits in coordination with something else. And you don't have to manually think about it. It's kind of like those RGB color programs, if you've ever seen it, where you move the mouse over and it changes a square to a particular color, and then it tells you the RGB code. It tells you the representation for it, so you can use that. So, adding personality, primitive states, examples, color, reflective, surface texture, stuff like that nature, specifying the vertices colors, and there's our RGB scale, which are red, green, and blue color combinations. And opening a window using GLET here. We had our simple GLET window example, and then we draw the scene from our display function, and then we start the loop. And then looked at the different parts, and essentially this part of the lecture was going through the different functions, such as main as an example, and then also looking at the init and what the init's doing. Init's essentially going to set our background color, our foreground color, and we're calling init here. So we create a, my mouse died. I have no mouse. Oh, there it is. We created, and we run init, and init is essentially going to, here we're going to clear the color. We're going to set the color. And then subfunctions to display objects in the scene. So here's drawing lines essentially. This is actually workable code that you can cut and paste and put into one of the simple. In fact, you could take the simple program if you wanted to and substitute in, and you can get a certain, like for example, this line here that's going to draw out on the screen. And drawing the 3D line. So we left it with the XY coordinates for the line, XYZ actually. Here's our XYZ, and then adding in the loop to close the lines together. Starting with the line width, essentially is another example, starting with the shape itself, and creating triangles and things, and closing the loop essentially between the lines. Again, that is one way of doing it. You don't have to draw lines. You don't have to draw points. You can draw shapes, primitives that are built in. So, which is kind of the interesting thing with OpenGL as a API. There's a lot of APIs written on top of it that are higher level, that take and create things with lines and points, because you have more control over it if you're not drawing a primitive and you're just using the line coordinate system. So, the concept of winding, I believe this is where we sort of left off, I think. Combination of the order and the direction for which the vertices are specified is going to give us our winding. So we can move things counterclockwise, clockwise, forward, back, all sorts of different positional things by drawing the shape in different orders. So OpenGL by default considers polygons that have counterclockwise winding to be front-facing. And why so important? Well, it's because you don't want to see the backside. So you can hide the back of the polygon altogether. So you can give it a certain color, reflective property, something of that nature. If you think about it, the humanoid that I drew had a front, a back. In fact, each one of them, each one of the sides of the head, each one of the arms had a front, back, left, right piece. And those were defined. You can actually get a shape, and this is another interesting thing. It's like leave out half of it, just draw the front, and then move it around. You see the back's hollow. So, if you've ever seen some really bad animation that doesn't refresh quick enough, you see the hollowness, and then it starts filling in. So some primitive, well, some from very old video games used to do that. In fact, they still do it, like old arcade games. You like see the guy, his arm moves up, but you see like the front, but the back part of the arm's empty. It's like a hollow box or something. It's kind of weird. It's because they just didn't draw it or didn't get refreshed fast enough. Which by default, if you just draw the face, the front, you're going to see the front. The back's going to be might be empty actually. The concept of the triangle strips and using a triangle strip with a triangle strip, which is nothing more than taking and adding more triangles that are it's positioned adjacent to the other triangle, which creates a strip as a concept. And that's a built-in primitive, the triangle fans. Let's see. Setting polygon colors themselves. In fact, that you can set each one of the pieces of the triangle fan to a different color, different shade if you wanted to as well. Setting a flat or a smooth or a shiny surface to your essential color is essentially applying a color and then applying a surface texture. So, and what I'm going to do in an upcoming lecture on color is go through the different surface textures for you so you can see what the effects are. So here's a four-sided polygon, or quads. I think this is where we ended up actually. So the general polygon itself, and then simple lighting is in terms of enabling lighting, we can turn lighting on and off. And keep in mind, I'm going to go through a lot more of this. This is the overview of the entire OpenGL package. I believe as soon as next week I start with the other lectures that are going to be on specific lighting, color, things of that nature. So, but in terms of the overview, we can turn it on, we can turn it off. We can enable different types of light sources. We can have multiple light sources in a particular scene. We can specify light source parameters as ambient, position, diffuse, and I'll be going through those in a future lecture. We can set global lighting for the entire room, spot lighting, mood lighting, all sorts of different types of lighting in terms of the model. And if anything makes a scene more realistic is the lighting, in my opinion. The lighting and the camera angle. Because if you have a lamp, and everyone's seen that, in fact, there's millions of examples of that little Pixar. Everybody has seen the spotlight, the desk lamp. If you've watched any of the old Pixar, it was like one of the first things that came out. And the interesting thing was the light that was moving. So the face of the head of the lamp rotated around. You saw the light go around, which was really cool. And it's actually, you can do that in OpenGL, no problem. What you're doing is you're taking a light source and you're positioning it at where the bulb would be in the lamp, and you're illuminating it. So you can show a lit bulb. So you can turn the light on and off if you wanted to. You can move the light around to cast the light. And these are just function calls built into the API, which is why a lot of people like OpenGL. It's very, it's extremely dumbed down in terms of its function. So, in terms of specifying the material, you can do the color, so diffuse color, material color. I'm going through all of the color attributes, and some of this lecture material is sort of a repeat because we've already seen some of the stuff already. But our OpenGL supports the two color models. We've got the RGBA model and the color index model. So we can go from the violet to the red scale, and we can also look at, as an example, the RGB as well. But here's our color cube, where it kind of mimics the hardware in some cases, and it kind of evolved out of monitor hardware color specifications, which is where the RGB came out of. So, in terms of color and shading, the color mode can be set, and we can actually color the shading, which is interesting. So, shade is kind of an interesting concept because it's darker, or it's off-white, or it's off-colored. So we can cast shades of different colors if we wanted to, make it opaque, make it transparent. In terms of the RGB color scale itself is the red, green, and blue. And usually, as the picture kind of reiterates my point, it kind of comes from what monitors were compatible with in the past. If you think about the concept, do you want to support something in a programming language that you can't see on the screen? It doesn't make any sense. So the model for color, the model for shading, everything, even lighting actually, comes from capabilities of monitors, tube monitors actually. Each color component stored specifically in a frame buffer, and then the frame buffer is rendered. So I'll talk about the rendering pipeline, and we'll talk about rendering graphics in a future lecture as well. In terms of color index, looking at from a color table, which is actually how graphic cards work. You know, there's a index that's associated with something that says we're going to cast this color. It looks up to a table that's stored in the graphic buffer memory, and the table translates it into something that is going to be projected essentially on the monitor. So we've got the scale that we can look at in terms of a lookup table and the frame buffer. Frame buffers are actually kind of an interesting concept, and buffering is a topic for an upcoming lecture soon. Actually, that's gonna hit. In fact, I'll probably cover graphic rendering, the rendering pipeline, frame, and buffering all in one lecture, probably, because it's all related. It's essentially making stuff seem, information that's being processed simultaneously, seem as if it's all appearing at the same time. And it's processed in a certain order, and it's rendered. And the image itself is actually rendered before it's painted. And then the order in which you're painting it, what you're going to buffer for animation, for more painting, is kind of tricky. And it could make something seem real or something seem jerky, so in terms of the effect. And it's only really an issue these days in terms of creating video games, which is what a lot of this stuff is used for, actually. You don't want your animation to be slower than your action or out of sync or something. So, color and state, GL color, vertices, color, vertex, some functions that can be done with that. Clearing the color, setting the color attributes themselves, clearing it, setting it to red. So, simple functions. Example of setting color in this particular example, I drew a triangle, and then we're setting the color. So, noting that the GL color function can be placed inside. So, inside of the begin, GL begin, and the end. For the particular shape, we can put the color in there too. So, two vertices of different color, blending colors. What happens if two vertices have different colors? Well, they're going to mix, or one's going to overwrite the other depending upon how the rendering is done. Shading, concept of shading, picking a shading point. So what color is the interior? We specify different colors for each of the vertices in the primitive. Well, it depends on which one's going to be brought up first or second. The second one's going to overwrite the first one usually. Smooth shading causes color vary as I go through different color cubes from one point to the other. So. The shading model is kind of interesting. Shading is actually quite easy. You apply a shading function to it. You can do flat shading. You can do transparent shading. You can essentially do a smooth, do a poly, do a full object shading, do a partial object shading. Smooth coloring is doing a transition, giving you this kind of an effect here, where it's not like a color with another color next to it. And it's back to back. So the transformation between this color and that color is smoothed. So this is an example of what they call default smooth shading. So it interpopulates vertices. So it's not a sharp contrast between one color and another. Alternative would be flat shading, as you've seen. So which is a fill color. So here's a flat shading, which is a contrast to a fill. So in terms of a smooth, this is not smooth, it's flat. So if you did a flat with another flat, you're not going to have this smooth transition between the two. And it depends on the type of object as to what you're going to apply. So, the Gouraud shading sets the a little bit more, so issues of color. So you've got combinations of color that exist instead of a smoothing. You have color combinations that are creating different colors given the RGB scale. Viewpoints as a concept as well. One of the things you can set in the OpenGL library is your viewpoint. The window itself, in terms of the plane, sets everything at 0. So you've got to rotate it in order to actually see the scene, which is kind of interesting. Because if you think about the concept, what we're looking at is a flat surface, but we're looking at it in 3D by rotating the flat surface to change the viewpoint in terms of the concept. And reiterate the point on event-driven programming and callbacks. As I mentioned before, you don't create these loops on your own. The OpenGL creates it for you. So virtually all interactive graphic programs are event-driven, which means the functionality in the API to take mouse clicks, to transform matrix, to accept input, and is an event-driven type of environment. So the graphics package is prepared at any time for input, any number of sources from the mouse to keyboard. And we have callbacks, essentially. So devices such as trackballs, joysticks can be put in there for callback action, which says, do something when this event occurs. So it's done through the use of callbacks. And the callback concept, and we had a callback, actually. We saw it in the Hello World. The callback is used when the graphics program instructs the system to invoke a particular procedure or function whenever the event intersect occurs. So saying a mouse is clicked or something, the callback function runs. And our callback actually was kind of empty, I think, in Hello World. So in your first programming assignment, when you create your windmill and your things, you create in the callback functions where you're going to put some primitive mouse stuff. Actually, I think it's the keyboard that it needs to do, like an escape key or up or down arrow key to rotate your scene. So when you're looking for ideas, look up callback event-driven programming on the internet or go to one of those websites and you'll see a ton of examples, and that's essentially where the functionality gets automated. The graphics program indicates its interests or its registers for various different events. So it involves telling the Windows system which event type you're interested in doing it, passing it the name of the procedure, and then write the handler for the event. So it's very much an event-driven, event handling type of environment. So there are different types of callbacks. Callbacks are used for two different purposes: for user input events and also for system events. If you're running a game, you use the callbacks to support the animation of the game. So the callbacks are going to essentially make your objects move all over the place and create that interactive type of environment. In terms of the user inputs, include things such as mouse clicks, keyboard clicks, motions of the mouse, moving to left to right, without clicking, things of that nature, also known as passive motion, and keyboard hits, or keyboard entries. So this is the program. So only signaled about events that happen in its window. So if you're not in the window, it's not going to know. So it's entering text into another Windows dialog is not going to generate anything. So we also have system events and display events. The system events themselves are a number of different events that might occur from the programming perspective: display, reshaping events, idle events, timer. We have timers. Didn't mention, OpenGL supports timers, so you can create animation through your transformation every 5 minutes, or every 10 minutes or something. Then you can create a pretty interesting screensaver, I guess, so, or any type of animation. The display event, in terms of when things are drawn, so every OpenGL program must handle an event that occurs in terms of the display when it's invoked. So it senses that the contents of the window needs to be redrawn, it will redisplay it. So. And refresh certain things. We also have an explicit request to redraw by doing a gloat post display procedure. Sometimes you want to redraw when something changes and you want to make sure it happens, and you don't, you want things to update, so you redraw it. So you don't want to redraw too much because then it could cause flickering actually in the event, or excuse me, in the callback. So types of callback, maybe reshape event happens whenever the window is made smaller or bigger, so the callback gets performed on the new size of the window. Maybe an idle event happens every time the system has nothing to do. You can use it for cleanup, clearing out buffers. If I've already loaded this, then I can empty it out or something. Timer events happens after the waiting period is over. The timer occurs. So here's an example of some of the callbacks, and this was actually taken from the Red Book, so you can go online to that website and actually kind of read through all the different callbacks that are associated with it. And here's some sample code that does reshape a mouse event, a keyboard function. This is where you're going to get your information for the first programming assignment, by the way. You're going to hopefully use this lecture as a resource to go through it and say, I have to do a keyboard event. Maybe I want a mouse function. No, I want a keyboard function. And then you go to the Red Book and you can find actually source code examples that will show you how to capture through the callback the keyboard events. Callback functions depend on the function that define what you're going to create. So here's an example of a callback function for software engineering. Well, what are we going to do here? MyDraw is going to display a window, and then we're going to reshape the window, and then we're going to redisplay it, and then we're going to have a timeout, and when timeout happens, we're going to redisplay it again. That's where you can create some interesting flickering if you wanted to. Actually, I've seen that done successfully in graphic scenes that are mimicking, you know those strobe lights that go around? Dance floors? If you created a scene that had a mirror ball and a strobe light, you could flicker it by constantly redisplaying it every 2 minutes or something. Get a really cool effect on your graphic scene, realism. You know those flickering that give people seizures, actually. You can give people seizures through the flickering of your OpenGL program by redisplaying every 2 seconds. And this is how you're going to do it. You can actually use a post redisplay to do it. So both the timer and the reshape callback invoke this function. And the function informs OpenGL that the state of the scene has changed, and you should redraw it. So redraw it. If you rotate it slightly and redraw it, that's where you're going to get that flicker. Yeah, here's some example of the mouse. Yeah, a little mouse activity. Here's some, the left mouse, the middle, the right. These are some GLUT parameters. Obviously, I can't give you all of them. This is just a sample of the most popular used ones. Keyboard input. This is what you're going to need to do for the keyboard input of the first assignment, actually. So as promised, that was the rest of this lecture. So in the coming weeks, starting next week, I am going to go through, actually hold on one second, well, I'll let you know next week. I'm going to go through each one of a series of topics, starting with some basic things that are sort of easy, like color, shading, lighting, and then I'll go into views, and then eventually towards the end of the course is when I'll cover the graphic rendering pipeline and some of the more technical stuff. It's not related to the programming assignments, because what I'd like to do is enable you or give you the opportunity to work on the assignments before the end of the course. So I give you all the OpenGL stuff first and all the assignment-related stuff. So, questions, comments, or concerns? I'll absorb that whirlwind tour. It is lecture 2A, because I know it's, oops, when is this saving? It is lecture 2A, so it's not bad. It's everything you ever wanted to know about OpenGL with not very much detail. So, if we don't have any questions, then we're done for today. If I were you, I would have the software installed. I'd have OpenGL running. I'd be going through some of the examples and maybe working on the first two assignments, which you could probably do at this point. So. And then you can also send me questions. You can say, hey, is this what I'm supposed to do? Because most of you, it's kind of like drawing, like when you first took your first art course, and you draw this thing. Is this what it's supposed to look like? So if you have questions and concerns about, is this what it's supposed to look like? You can always send it to me. And if you're using the same software as I'm using, the Dev C++, then all you have to do is send me the source code file. I can load it up into a project and I can run it just fine. So. Okay, so unless we have any questions, we're done for today. We will have class next week. I don't expect to miss any more classes towards the end of the day. So we're on schedule. So. You guys are so quiet. You think you're tired. Okay, we're done. Bye-bye. See you next time.